as promised, we're here to graph a function. So I've given us the function f of x equals x e to the x, and I've asked us to graph it including all of the following. Intercepts, so that means x and y intercepts. Horizontal and vertical asymptotes, if there are any. Okay? I may ask you to check for things. They may not exist, but I want to then see the work for checking. Okay? Maxes and mins and points of inflection. With both of these, make sure we're going to label our x and y values. Okay? And the written directions that you're likely to encounter on a quiz or an exam would say make sure that your function is increasing and decreasing and concave up and concave down on the appropriate intervals. I didn't bother to write out those directions just because my board is so small, so I figured I would just verbally give you those. Okay. All right, so basically this information I'm going to get from f, so I'm going to start with that. Then I'll get this information from f prime, and I'll get that information from f double prime. And this is going to be a long process, so every time I find something, I'm going to add it to my graph. So if I start with my intercepts, let's get our y-intercept. So I know that's just 0, f of 0. But if I plug in 0, I'm going to get 0 times e to the 0. I'm getting 0. So the y-intercept is just the origin. X-intercepts, or septs, I know those are the places that are on the x-axis, which means the y value is 0. So I would set x e to the x equal to 0, and that would mean either x is 0 or e to the x is 0. Now I've already got the point where x is 0, and I know e to the x is never 0. Okay. So turns out the origin is my only x-intercept. That actually gives me a lot of information right there, because not only do I know that that point is on the graph, but I know that I don't cross either axis any other time. Okay. All right, so let's check for asymptotes. Okay. If I start with horizontal asymptotes, that means I'm looking at the end behavior. So there are two limits I need to evaluate. The limit as we go off to negative infinity, and the limit as we go off to infinity. If I look at the limit as x goes to negative infinity of x e to the x, this is looking familiar. I think we might have had this as a previous example, but let's do it anyway. That's going to go to negative infinity, and that's going to go to 0. So I've got an indeterminate product. I'm going to rewrite that as the limit as x goes to negative infinity. Keep the x there, write that as e to the negative x. I want to move whichever piece I can move without making its derivative much more complicated. Okay. Because now I can L'Hopital this, so this becomes the limit as x goes to negative infinity of 1 over negative e to the negative x. Okay. Now, the denominator here is going to negative infinity, so the whole thing is going to 0. So that tells me that this is a horizontal asymptote. So it doesn't give me a point to put on the graph here, but it does tell me when it's time to play connect the dots, I need to make sure that I end up very close to that x-axis. Okay. Let's check on the right-hand side. Limit as x goes to infinity of x times e to the x goes to infinity, e to the x goes to infinity. That's infinity, no asymptote on the right. Now, I asked to check for vertical asymptotes, so let's just check for two things. Well, I don't have a fraction, so there's nothing to make the denominator 0 because there's no denominator. My building blocks were just x and e to the x. Neither one of those has a vertical asymptote. So I can simply say there is no vertical asymptote. But I want to get in the habit of checking for that to see if there is one or not. Okay, so that's all the information I'm going to get from f. Let's move on to our first derivative. So I can say f prime of x. Now it looks like we're going to be using product rule here. So that's going to be the derivative of x times e to the x plus x times the derivative of e to the x. Derivative of x is just 1 times e to the x plus x, and the derivative of e to the x is e to the x. Okay. Now, that is always defined, so I won't have any critical numbers from it being undefined. I want to set it equal to 0. So e to the x plus x, e to the x equals 0. I want to factor out that e to the x. So we get e to the x times 1 plus x equals 0. So either e to the x equals 0 or 1 plus x equals 0. Now I know e to the x is never 0. So it must be this one. So x is just negative 1. Okay, so I'm going to draw my number line for f prime. I'm going to mark off negative 1. That's my critical number. And then I'm just going to pick some test numbers. So if I pick, let's say, negative 2, if I plug that into the derivative, and I prefer to plug into the factored form, so that's just the left-hand side here of this equation, that's always positive, but 1 plus negative 2 would be negative. So I know my function is going down. And then to the right of negative 1, I can just plug in 0, which is kind of nice. And if I plug in 0, I'm going to get e to the 0 is 1, that's positive. 1 plus 0 is also positive. So my function is going up. So that tells me that I'm going to have a min at negative 1. Now, negative 1 is just the x value. I want to know how low down does that min actually go. So I need to figure out the value of the min. So I need to plug that in to f. Not to f prime, but to f, the original function. So when I do that, I'm going to get negative 1 e to the negative 1, or negative 1 eth. That's a negative number. I'm going to plot it below the x-axis. I know e is between 2 and 3, so this is between a half and a third. I'm just going to put it here. I'm probably not drawing things perfectly to scale. I'm trying to keep it from being too close here because I want to be able to see what's going on. So I'm aware that I'm not drawing this perfectly to scale, but I'm going to go with that. Okay, so now we're ready to try to find points of inflection and the intervals where we've got different sorts of concavity. Okay. So we just figured out that f prime of x was e to the x times 1 plus x. I kind of like that factored form for taking the second derivative as well. I could keep it in this form if I wanted to, but I'm going to have to use product rule either way, and so that gets rid of the whole thing in one shot. Okay, and you know what? I'm going to just copy that a little bit smaller so that I have room to put my number line for the second derivative below it. Okay, so f double prime of x is going to be the derivative of e to the x times 1 plus x plus e to the x times the derivative of 1 plus x. So derivative of e to the x is e to the x times 1 plus x plus e to the x times the derivative of 1 plus x is just 1. Now with an e to the x in both terms, I'm going to factor that out, and that means this is e to the x times x plus 2. Okay. Now that is always defined, but I want to see where it could be 0 because that's where it could change sign. So e to the x times x plus 2 equals 0 means e to the x is 0, except I know it never is, or x plus 2 is 0, which would mean x is negative 2. So on a number line for f double prime, I'm going to sort of line things up. Negative 2 would be to the left of negative 1. Picking a test number of negative 3, if I plug that in, e to the x is always positive, but negative 3 plus 2 would be negative. To the right of negative 2, I think I'm just going to plug in 0 because it's easy. So then I'm going to get positive times positive. And notice that's consistent. We said we had a min here. Well, at a min, we should have a concave up graph. So we're concave down here, concave up here, and so we're going to have a point of inflection when our x value is -2. But if that's a point, it has a y value as well. So I want to plug in, and what I'm going to do is calculate f of -2, because I want to add that to this graph, and this is the graph of f. Okay. So f of -2 would be -2e to the -2, or -2 over e squared. Okay. Now, I know that that's negative. Okay. How big is it? Well, it's, let's see, this was a min. I'm going to draw in a little thing there to show that. It's higher up than that. It's negative, so it's lower than the x-axis, but we're going to hit that on our way down to this min, so it's got to be above here. Okay. So I'm not drawing things perfectly to scale, but I can say, okay, that point right there, there's -2 over e squared. That's going to be my point of inflection. So now we're ready to play connect the dots. Now we've got 1, 2, 3 dots, but we've got a whole bunch of information, because I know that this is a min, I know that this is a point of inflection, and I know I have a horizontal asymptote here. So I've got to start out close to the x-axis. I can't start above it though, because I've got to end up below it, and the only place I'm allowed to cross it is over here. So I'm going to start out close to but below the x-axis, and I'm going to just be going down and concave down until I hit that point. You'll notice, in order to be concave down, I have to sort of adjust that point a little bit. When you're not drawing things perfectly to scale, sometimes you do have to adjust a little bit when you're trying to draw things. Now, at this point, I'm going to switch to being concave up, pass through my minimum point there, stay concave up and increasing as I pass through that point. So now I like to, once I've graphed it, do a quick check, just comparing to my number lines. Did I go down and then up? Yes. Was I concave down and then concave up? Yes. You want to be very careful. It's sometimes easy to say, oh, this was such a long problem, thank goodness I'm done. And you just changed the concavity. So, and if you haven't drawn things exactly to scale and you're connecting the points, sometimes you inadvertently change the concavity to hit your points. You want to adjust so that you can respect the concavity that you're supposed to have.